So now we will look at angular momentum, but before we do that, we look at just a quick review of linear momentum, which we have done earlier, which is written with the letter lowercase p, which is m times v, and the units are kilograms meters per second. So if we have an object of mass m going in the direction v, it will have a momentum in the same direction. Now let's consider an object that's a cross of equal sides. All sides are considered equal. Its mass is extremely small, so we'll ignore it. And there are four masses of equal value, four equal masses attached to it. And this thing is spinning, so this velocity is v, well, the speed is v, this speed is the same, they're all moving with the same speed. The velocity of this one is to the right and velocity of this one is to the left, and they all have the same mass. And they all have the same r. Now, the linear momentum of this one is going to be mv, and it's going to be to the right. The linear momentum of this one is going to be mv, and it's going to be to the left. So the sum of these two would have zero linear momentum. Similarly, the linear momentum of these two would exactly cancel out, and so if we get the sum of the linear momenta of these four particles, that's going to be zero, even though each of them does have a linear momentum, but the sum is zero. And that's okay because the center of mass is not going anywhere, they're just spinning. If the center of mass were moving, it would have a linear momentum. The center of mass is stationary for the whole system, and therefore the linear momentum is zero. Now let's say this is, it may be spinning or it's initially stationary, and we apply a force. And that force will cause it to start moving and create a linear momentum. And we know that the force is going to create a rate of change of linear momentum. So when we apply this force, this gains linear momentum, but this gains an equal and opposite momentum in the opposite direction, and it cancels it out, and so do these two. So we are applying a force, but the linear momentum of the system is not changing, and that apparently contradicts what we've been doing before, that the force is a rate of change of linear momentum. We do have a force, but this side is not zero, but this side is zero for the whole system, not for one particle. So let's try to resolve this, and we say that let's find the torque, which is r cross p, r cross f. Okay, so we have a torque which is r cross f. So we have an f and we have an r. The r cross f will be a torque. So this torque is applied on this object, and that's going to be r cross f is dp by dt. Now since r is, it's a rigid body, so the r is constant and it's going to be spinning, so r is always the same, so we can take it inside, becomes d r cross p over dt. Okay, and it can be shown that this and this are the same, which is true only if r is constant. R cross p is called angular momentum. So the linear momentum is when an object is just moving in a straight line, and angular momentum is that linear momentum times an r or cross an r, and it's used for, mostly used for spinning objects. The units of angular momentum would be meter for r, and the linear momentum would be kilogram meter per second, so it's kilogram meter square per second. That would be the unit of angular momentum. So if this is angular momentum, and that's written with the letter L, that's the symbol for angular momentum. So we have torque equals dl over dt. So just as we have F equals dp by dt, the force is the rate of change of linear momentum, the torque is the rate of change of angular momentum. So now we have a force applied at a distance, so we have a torque. That torque is going to change its angular momentum. So it's going to start spinning faster and it will gain angular momentum as a result of that torque. Individual particles will gain linear momentum, but the system's linear momentum will not change if it remains spinning, if the center of mass does not move. Now this angular momentum is r cross p, which we write as r cross mv, and we can also write this as r mv sine theta, because r cross p would be rp sine theta and this would be r mv sine theta. Now let's consider a case where we have somebody holding a string with a mass, and that mass is going around in a circle. Okay, so it's going around in a circle. This radius is r, the mass is m, and at this instant it has a velocity v. So the angular momentum of this stone about this point, and we won't always have to say about which point, because the angular momentum would be different about different points because r's are different. So it's going to be this equation, which is r mv sine theta. Sine theta is the angle between r and v, which is 90 degrees, and sine 90 is 1. So the angular momentum is going to be mvr, well, rmv or mvr. We just write it as mvr. This will be the angular momentum of this stone as it's going around in a circle. And well, we don't have the direction here because it's just a magnitude. The direction will be perpendicular to both r and v, which means it's going to be coming out of the page. Now let's consider in the same situation that we have another object, and this one I'll make with a red colored pen, and I'll make it a square just to differentiate with this mass. And this little square is following the same path. It has the same velocity as v, and as it keeps going, it would have passed exactly through this point and kept going straight just as this was going. And well, we're assuming that this is no longer here so that it can keep going straight. So when this object is right here and moving with the same velocity v, then about the same point, it's at the same distance, so it will have an angular momentum of mvr if the mass is also m. Well, that's it's not turning around it, it's just going straight. But the equation written over here just has an r cross p. It does not require the object to be going around it. It just says distance times the linear momentum, or distance times the mass times the velocity. So this has a velocity, it has a distance, it has a mass, and so it has the same angular momentum as the object going around in a circle if the mass and velocities are the same. So that would be its angular momentum of this mass when it is here about this point. So what is the angular momentum of this object? Is coming from behind. What is its angular momentum when it is right here? It still has an r and an m and a v, so we must have some kind of angular momentum. So let's join this together. This becomes its r, or it should be right to the center. That's this r, that's the v, and the angular momentum is going to be r, capital R, cross its p, which is going to be r m v. Okay, p is mv, r is r sine theta. And now the theta is going to be this is going to be r, and v, theta is going to be this angle. And sine of this angle is the same as sine of this angle. Okay, and r sine phi is simply, in this triangle, r sine phi is little r. So this is going to be rm. Well, r sine phi is little r, so it's rmv is the angular momentum of this object when it's here. So when it's here, its angular momentum is mvr. When it's here, it's also mvr. Okay, written the same mvr, not capital R, but this r. So the angular momentum of this object did not change as it moved along. The r changed, the v did not change, the mass did not change. The r kept changing, but the r sine phi always remained the same, unless of course it turns. But if it goes in a straight line, the angular momentum does not change. And that's a sort of indication towards the conservation of angular momentum. And here we have the law of conservation of linear momentum and the law of conservation of angular momentum. So let's just review that very quickly. The law of conservation of linear momentum which is that in the absence of an external, or rather of a net external force, okay, there could be forces but they all add up to zero. In the absence of a net external force, the momentum remains constant. Okay, or if f is 0, then dp by dt, well, is also 0 because f is dp by dt. So similarly, the law of conservation of angular momentum is that in the absence of a net external torque, the force is replaced with the torque. The angular momentum, the p is replaced with the angular momentum, remains constant. Or the sum of torques is 0, implies dl over dt is 0, or L is constant. Now, let's go back to the angular momentum of this mass, m, with the speed v at distance r, and we found that L was mvr. Now we rewrite this as knowing that as it's going around in a circle, v equals r omega, where omega is the angular velocity. So it's going to be m, v is going to be r omega, r is going to be m, the two together, r square omega. And we know that mr square is the moment of inertia of a point mass. So L can be written as I omega. So that's another way of writing the angular momentum. It's equal to mvr, it's equal to I omega. And this is very useful when we have a solid object, and we use that to write its angular momentum. Now, if we have, for example, the previous case where we had 4 objects, then and it's spinning like this, then the L would be the I omega, which would be the moment of inertia is mr, the sum of the miri squared times omega for all the particles. And well, if we write this as as before, that the torque is R is dl by dt, and L is I omega, then this becomes d by dt of I omega. And if the moment of inertia does not change, then that can be taken out, and it's d omega by dt, which is I alpha. So we have torque equals I alpha. And this equation corresponds to F equals ma. So that's F equals ma in linear motion, and that's torque equals I alpha in rotational motion. And the law of conservation of momentum would state that if the next external torque is 0, alpha is 0, which means omega is constant, and the thing will keep on rotating at a constant angular speed, which would mean that I omega would remain the same.